All right, good morning, everyone. Thank you for joining me today. This is a webinar on the Goal Seek and Control module titled Goal Seek and You Shall Find. It's an introduction to the Goal Seek and Control module, also known as GSC. So let's get started. It is an add-on module for both AFT Fathom and AFT Arrow. So if you are users of the software, you understand that these are two different base softwares, and GSC is an add-on to that. So that means it's sold separately from the base software. So you might try to go activate it during the webinar or after the webinar and see. You may not have access, but we'd be happy to help you out with that. I put the contact information at the end of this show, so you should be able to reach out, no problem. Give you a little background. So I am a business applications engineer over at Applied Flow Technology. We are a world leader in fluids modeling and analysis. So essentially what that means is it's software that models the flow in your pipes. You've got flow going through your systems, and we take that and put it into a computer so you can simulate and do different analyses and compare different scenarios and things. So AFT Fathom is one of the base programs that models incompressible flow at steady state, and AFT Arrow models compressible flow at steady state. So that would be like gases, and Fathom would be more akin or more useful for liquids and very low velocity gases, assuming it's incompressible. But we don't just sell software. We are heavily involved in the hydraulics community overall. We are involved with HI standards and codes, involved in education, academia, and we work with Engineers Without Borders. So that's a little background on us. And before we get too far, let's talk about safety. Do a little safety second. Protect your hearing. And I bring this up because process plants are very loud. And you may have an office job, which is why you are able to watch this webinar live, perhaps, but you likely have to visit your real systems in action. So don't forget the importance of protecting your ears. And it comes up a lot if it's not your daily job to be in the plant. Often you may neglect that a bit. But standard ear protection is cheap, unobtrusive, and a no-brainer, kind of like GSC is a no-brainer. All right, so an overview today. We will go over some goal-seeking theory, a GSC module specific example and how to use it and the proper technique for this module, how it ties back into control, because it's not just a goal seek module, it's goal seek and control module. Okay, then we will look at GSC for Fathom versus Arrow, because we've got people who use both programs, we've got people who use one of them, so it helps to go through both, even though it's the same idea. We'll go through some troubleshooting. If you run into any problems using GSC, it's helpful to know how to fix it. And we'll finish with a case study of someone using GSC to analyze their own system. So what does it mean to goal seek? When we talk about goal seeking, I think in the younger generation, we use a lot of computers and we kind of understand this idea of goal seek, whether it's in software, something like Excel, but it's not always intuitive. So it's good to kind of break it down into bite-sized chunks. And I like to always start with the goal in mind. So what is your goal? Kind of like motivational speakers will tell you, start with the goal in mind, and then we'll figure out how to get there. Right? You have a desired output value. That's what that means. So there's some value you have in your mind that you want to get to. This is user specified. Okay. Then we need to vary the inputs until that desired output is achieved. That means we need an initial guess, and this can be a manual or automated process. So again, changing inputs to get a desired output. And the variable inputs must actually impact the output, and that means, in other terms, the output must be a function of the inputs, because if we're changing inputs that have no effect on the output, we're not going to get anywhere, right? Okay, so that's just an overall view of what it means to goal seek, and this theory, not just applying to AFT software, but in just any space, any software or life space, goal seeking follows this process. So let's go through an example not related to hydraulics or fluids, just so we can kind of warm up into this and get a better idea of what it's like for in a real world example. So my goal is, oh, I desire $1 million. That would be excellent. That's my goal. We started, talking about motivational speakers. Why not? I want $1 million, okay? This goal to me is a function of 3 known variables. These are not all of them, obviously, but these are the ones I chose. 1, age, work ethic, and inheritance. Those are the 3 variables I know that this goal is a function of. But I don't have control over 2 of these really. Age and inheritance, I don't really have control over. At least I hope I don't have control over inheritance. That has some bad implications. So I'm going to only worry about varying my work ethic. Again, goal, $1 million. My variable, my work ethic. So let's see what happens, okay? My initial guess of work ethic is 50% capacity. This is my sort of daily operation, let's say. I just work at 50% of my capacity and my time and all of that. So that's where I'm going to start off from. Okay. I'm going to vary my work ethic in several ways to see the outcome and to see if I actually reach my goals, or my goal, singular, $1 million. If I work less, let's say we go down to 25% of my work ethic capacity, I get further away from my goal. Okay, so that wasn't great. If I work even less to 10% capacity, I'm even further away. So clearly I'm moving in the wrong direction. Okay, well, let's now go on the other side. If I work more than my 50% capacity, I'm getting closer. If I'm at 75%, I'm getting closer, but I'm still not there yet. And then bingo, I work a lot more, working 20 hours a day and just cranking out productivity. I have reached my goal. There we go, varied inputs to get my desired output. And I finally reached it after a few iterations and a few years of good financial planning. And you may be thinking, well, working less was kind of an obvious move in the wrong direction, right? Especially if I did it twice. So it's not exactly the most common way to obtain $1 million because unfortunately, we can't all live like Peter Gibbons. And if only one of you gets this reference, this attempt at a joke was worth it. So again, you might be thinking, well, why'd you even go in that direction? And that's where constraints come into play and user intuition with using, doing anything related to goal seeking. I could have decided up front that going below a certain capacity wouldn't help, right? That's what I would call putting on a lower bound on my iterations. There's no need to go lower and waste time in iterations if it's not going to get me closer to the goal. Again, user specified, so I would have to know that up front, kind of use intuition, you can say. And there can also be a smarter way to search rather than just randomize plugging in values. So again, I could have recognized that my first move got me further away from the goal. Why would I go for a second time, right? Could have changed directions, gone back up. So this is what I would call intelligent searching rather than randomized searching, intelligent. And that's the power of GSC. So what is GSC? The module, we went through just a life example. Well, let's look at GSC specifically in AFT software. After all, that's why you guys came. It's called goal seek and control. So we kind of went through some of the goal seek part. We'll go through control a little bit later. It's an add-on module for both AFT Fathom and AFT Arrow. Again, 2 separate base software programs. And they must be this. The GSC module has to be the same version as the base software application. This is just for you users out there. If you, are doing a trial or a lease of a module and it doesn't correspond to your current version, you will not be able to use it. And again, it's sold separately, so some of you may not have even had it from the start. I hope I can convince you to get it because it really is a no-brainer to me. It automates the process of changing input variables to achieve desired design goals. So it automates it. What we were doing earlier was doing manual iterations, right? Goal seeking, like in the previous example, and it extends Fathom's control modeling capabilities to include controlling a remotely located variable. That's kind of a mouthful, but essentially, it allows you to control parameters that are not able to be directly controlled by control valves, things like that, especially when they're in remote locations, like way downstream. What about temperature? Things like that. Again, we'll get into it. But the point is GSC automates this process, and it's just up to the user to define your goal and then to define the inputs you want to vary to get that goal. But the first part is the goal seek. The second part is the and control part. See how it fits together? After a few examples, I'm sure it'll start to click a little bit more how they're related. All right, so it works, it operates much like that in the previous example, except that it automates the process, right? You can vary multiple parameters at once, and that's a very powerful thing about GSC. I can sit here as a user and just plug in different numbers and try to get my output right, but when I have to vary multiple parameters, it becomes very difficult. And it uses intelligent search, again, not just randomized plugging in values. And the GSC module employs numerical optimization technology like that used in the automated network sizing ANS module. It's an optimization engine employed by the same optimization engine employed by AFT Fathom GSC. And it uses the state-of-the-art optimization technology from Vanderplaat's research and development. So it's this, we kind of leverage this optimization engine from Vanderplaat's, and we use it in GSC and ANS. And GSC is very similar to ANS in that you have a desired output and you vary something to get it. But I want to give a little plug for ANS since it's a new module and you may not have heard of it yet. Again, it's the same add-on idea for AFT Fathom and AFT Arrow. It works for both, okay? You can visit the website to learn more. But again, it's brand new and it's really even more powerful than GSC in that it's you can specify an optimization goal for your entire network, like having the lowest cost system, lowest weight system, what have you. You provide the design requirements to guide the solution. So my goal is some optimum goal. Then I put in some constraints like a maximum velocity. Maybe I need a minimum pipe size. And all that, and it varies pipe diameters to find the size that achieves your optimization goal, again, as a network. So all of your pipes, and it is quite versatile and very customizable and quite powerful. I just wanted to bring that up. Well, and in a matter of seconds, it will provide a design for your entire system, just a plug for you, as it is very related to GSC and its search optimization. Okay, so back to GSC goal seek and control. The core hydraulic solution in AFT Fathom is performed by what we call the hydraulic software. This is what runs when you are just doing a steady state simulation in Fathom. You click run model and you see this window pop up, a bunch of numbers flying around. That's the hydraulic solver. So it is only called once to solve a system because there is one answer to your steady state and it's not trying to perturb variables to go to a different goal. Not yet. In just the standard hydraulic solver, it is solving the system at once. Okay. GSC's numerical optimizer is used to call the hydraulic solver repeatedly. So it does it once, solves a steady state, then it perturbs the variable to see what changes were made and to see if we've hit the goal. Again, adjust variables to force the hydraulic solver to agree with user specified goals. So here's a little flow chart of what that looks like. Let me get a pen. So in just your standard steady state Fathom solver, we've got input, it runs through the hydraulic solver, and then it goes to output. After a few iterations, similarly, it does iterate because it's still a numerical solution, but it sticks around in this box usually, okay? When we turn on GSC, let's get rid of these. It goes into the hydraulic solver, gets an answer, tries to see then, did it match the goal that you had specified? No? Okay, well then it keeps running. So GSC calls the hydraulic solver multiple times until it gets within a certain tolerance of the converge, to get an answer converges on a solution that's within a certain tolerance and then pops to the outputs. Okay. So there are a few types of GSC goals that can be specified. Again, all user specified. There's a point goal, where the desired goal is at a specific location in the model. Differential goal is a goal that describes a difference between two variables, so maybe a flow rate across two parallel paths. So it's the difference, right? And it's defined as the value of object 1 minus object 2. That will come into play when we actually go through an example. A group goal is a goal defined to a whole group of objects at once. And that one is a little different, a little special. We'll have to go into more detail with that a little bit more later. So I just wanted to present the 3 different types you will have and you may see in the interface. So they all have, the group goal has to have the group already made, and we'll get into that again. So let's start with an example, get our hands dirty with GSC so that we can create tangible understanding from all of these words that I'm speaking. And it's time to get specific with fluid mechanics, as a lot of you are probably fluids engineers or some sort of engineers that deal with fluids. Let's get into it. Okay, I have a goal of 200 gallons per minute of flow through this simplified system. Okay, I've got 100 pounds on my upstream, downstream is 95 pounds, and a 3-inch orifice between them. So what can I do to get 200 gallons per minute? Because it's unlikely that this system as is actually going to give me 200 gallons per minute. Well, it's an excellent question. So let's launch up Fathom. I'm just going to start from a base model so that those of you who may not be as familiar with Fathom or using our software in general can watch how it's launched up and understand the process of building a model, kind of a twofer in here. But again, this system as is may not actually give me 200. So I have to then think of variables I can change to get my goal. All right. Well, let's just start off the bat, building the model. Okay, I've got a blank workspace. Again, I've got pressure upstream, a pressure downstream. If you didn't know, Fathom 11's got the new feature where you can double click a junction and you can place multiple of them on the workspace. Pretty nice. I've got my orifice between them and my pipes connecting them, right? Okay, so I built my model. Now I have to define my junctions and my pipes. And before I do that, I like to use the show object status because then it shows the different junctions and pipes here in red to tell me that they're not defined yet. I also need to define my system properties. I will use water at a whopping 60 degrees Fahrenheit. All right, so now let's go in and define my pressures. As I said, I want to use static pressure because those are the common pressures you'll measure in the field. It's the thermodynamic property of pressure, and the difference between stagnation and static is a discussion for another time. But always enter in your elevation first. I forgot to do that because it copies the elevation with each junction and makes it a little faster. So if you do it with the first one, it's a lot better. Okay, so 3 inches. Oh, can't get a K yet because I have not defined my pipes. So again, let's see, steel. I want cylindrical, obviously. 4-inch, 20 feet because it's 20 feet on each side of the orifice. And the cool little feature, if you've never seen it before, is you can copy data from another junction or another pipe. I want all of it because they will be the same, 20 feet of length, 4-inch. Okay, great. Now you can see there's no red. I'm ready to run the model. So I need to save it first. Let's go. Let's see, beginning. Okay, now that I've saved it, it will allow me to run. So here's that hydraulic solver I was talking about. This is just running it in steady state, haven't done anything special. Well, that's not good. That would be because I didn't put in the right pressure. There's some troubleshooting for you. My apologies. Let's run that again. Hey, we've got some flow. Excellent. So as you can see, we have not reached our goal. Our goal was 200, and right now we're at about 475 gallons per minute. Okay. So let's make a profile graph so we can talk about pressure and some hydraulic theory while we're in here. So it's always good to go through that stuff. Makes things a little more tangible and applicable. All right, I'm going to change my graph. Oh. All right, I'm going to save this as a graph template. If you've never used this before, I strongly recommend it because then you don't have to recreate the same graph for each scenario you make. So what's going on here is we've got pressure drop and then we've got this orifice. So if I turn on my junction, J3 is my orifice here, that's where you see that large pressure drop. And then we've got pressure drop from friction through the rest of the system. And this orifice is a major player in determining the flow rate, because if I have more pressure drop from this orifice, I will have a lower flow rate, more resistance in the system. I will also have a shallower slope here so that there's less frictional losses because there's a smaller velocity. So just some theory there. Now, let's go back to the PowerPoint and really work through how we could use GSC for this. Okay, so what could we vary to get 200 gallons per minute? Well, you might be thinking, why not change the orifice size, vary that? Excellent idea. Let's do that. Okay, and always with your system, use intuition and make sure to run it at steady state without GSC before moving on to make sure it's runnable. We will talk about that more when I get into the technique of GSC. Okay. So again, intuition, can I even reach 200? Right now, yes, I can, because I'm about 475 gallons per minute, which means if I just put in more restriction, I can lower my flow rate. That's probably a real solution. So GSC, let's do orifice. Okay. So to turn on the module, that's probably a good starting place. Activate modules here in the tools window. GSC, I want to check it on. So if you don't have a GSC license, when it says it's checking right there, it will just return an error saying you don't have the license. That's when you know you need to contact AFT so you can get yourself a license. Then we need to turn it on. It defaults to ignoring it, but we want to actually use it, so I'm going to use it. And here is where the magic happens. Goal Seeking Control Manager. Okay, so you see variables up here, goals next to it, and numerical control don't touch until you've talked with someone at AFT or you've listened to my troubleshooting stuff. But usually you stay within these two different windows. So my variable, I want to vary my junction orifice, right? So that's the number, diameter area. See how it says diameter / area? Okay. How do we know which one it's trying to vary? It's because it depends on how your system is defined. You see, we could have defined the orifice as an area or diameter. Well, I chose diameter with these units, which means this variable is going to link up to that. There's no need to specify it anymore. It just takes the data already in the junction. Okay, my goal point, I just want a point goal because it's at a certain point flow rate of 200 gallons per minute, and I can choose which pipe. It doesn't really matter because it's only a one-path system, so I will just choose pipe 1. Okay, now here in the interface, you'll see a G and a V here, and you guessed it, that means my goal is a flow rate through here, and my V is the variable, which is my orifice. So let's run it. So you can see down here, you have an extra line about in this hydraulic solver, and that's how many times AFT or Fathom went through the hydraulic solver to finally converge on the variables that give me my defined goal. So up here, you see 2 new tabs in the output area, GSC variable, GSC goals. So I met my goal, 200 gallons per minute. My variable was the orifice diameter, and it turns out a diameter of about 2 inches gives me my flow rate, and I had defined it earlier as 3 inches, so I was a little high. Okay, now let's look at that profile graph. Here we go. So if you remember before, we had a lot steeper slope here. Now we have a smaller slope, right? But the same pressure gradient going from 100 to 95 pounds. But this orifice has a much larger pressure drop across it, more resistance. causing a lower flow rate, and that lower flow rate is represented here by a shallower slope because it is not moving as fast to cause as much frictional effects and pressure drop. Okay, very cool. Now let's go back to the PowerPoint. 19. So what other things could we vary to get 200 gallons per minute? Not just orifice size, right? Now we're getting into some hydraulic theory. I could vary my pressure, my driving force, right? If I change my driving force, I could also potentially get 200 gallons per minute. Elevation changes, very related to pressure, changing my grade line, right? What about pipe friction? Could I achieve or get enough friction in my pipes to cause 200 gallons per minute instead of 475? Certainly is possible. Now we'll see if it's realistic. So why don't we go through and actually build that out? And I'll give you a rundown of Scenario Manager too while we're at it, because that's what I'm doing, Scenario Manager. If you never use this, please use it. It's a great way to organize everything. Any change you make in the base scenario will be reflected downward. GSC, okay, I want to change my pressure. Now, because I made the scenario from my base, I still have to turn on GSC because it wasn't on for my base, and it's a direct clone. So now I have to actually turn it on. But then I get into my manager, and you can see the apply button is unchecked here. Same with the goal, even though it's the same goal I had defined earlier. But that's because this is a new scenario, and it assumes you do not necessarily want the same variable and goal applied. I could, right? I could just check it right there. Or I could go through and add a variable specific to this scenario. Okay, let's do assign pressure. I'd like to do my downstream pressure. That seems variable to me. Okay, but my goal is the same. Now, in our numerical control, we've got this new thing where we are defaulting to the beta method, but we really should use least squares here. I know you might be wondering why. It's just a better way of solving for it with only one variable and one goal, but that was the default. So anyway, when you actually go to use this, you probably won't see that, but if you do, you can always contact us. Anyway, what I've got here now is a different variable going to the same goal. Hey, there we go. It ran 77 times, okay. Perfect, looks like good, no errors. My variable, 99.1 pounds downstream. Wow, that's not much of a pressure gradient if you ask me, but that's what's required to get the same flow rate if my orifice size is still the 3 inches that I had before, right? Okay. Now, let's vary the elevation. So again, I created my scenario from the base, so I have to turn on GSC, okay? Go into the manager, you can see my 2 variables I put in before. Well, now I want a different one that defaults to being applied. Assign pressure, sure, let's change the elevation of that, but not the pressure. So here is where I can define which parameter I want, right? I want elevation. I want to vary elevation until I get my goal of 200. Again, going to go back to least squares. There we go. Okay. And here the theory is, even though I have the same orifice size, maybe if I flow uphill, I could get a lower flow rate than before. And what? There it is. If we start at about 10 feet lower than my baseline reference level, and I'm pumping up or having some driving force upward, I get 200 gallons per minute. Okay. And for that other profile graph with the pressure differential so small, 100 to 99, you really wouldn't see much. I should have showed you, and I'll go back to it. But here we go. This is a very different graph than we saw before. And that's because the static pressure, it looks like there's a lot more pressure drop, right? And there is, but it's not coming from friction anymore because now we are not at the same elevation. A lot of this pressure drop you'll see is caused by the increase in elevation. So you have a much higher pressure at the very beginning and you're going up. So not only do you have pressure loss from friction, but you also have pressure loss because you're going up in elevation. So again, just going through fluids, theory, because it always helps to understand that before you go into GSC. Lastly, we are going to vary pipe friction, keeping all of the other variables the same. So this scenario is assuming I haven't changed anything yet, right? Okay. Goal seeking control, new variable, junction. Ooh, I don't want to vary a junction anymore. I want to vary a pipe, because remember, there are two objects to AFT software. There's pipes and junctions. So pipes are what connect junctions together. So pipe, okay, P1, sure. I don't want to change the design factor. I want to change the friction or the roughness. That's what it will actually be varying to get my same flow rate. Oh, go back, make sure it is least squares. Woo, that's some friction. 2.5 inches of roughness to get 200 gallons per minute. Yikes. Well, that actually makes sense. You have to increase your friction a lot to slow down the flow so much. I mean, you could see that going from 100 pounds to 99 pounds was the proper driving force for 200. Well, if we're going to 95 pounds, we need a lot of friction to prevent that. Now let's go look at the graph. Hey, it looks so similar to that last one with an elevation change. This time, it's a different reason for such an extreme pressure drop in pipe 1. Last time, it was because of an elevation gain. This time, the pressure drop is solely out of friction. With such a large friction factor, we get such a large pressure drop, and the orifice doesn't cause as much of a pressure drop because it's a lower flow rate now. Okay. Oh, and I promised you I would show you the graph from changing the pressure driving force from 100 to 99. It's very small. You'll see that here. But all we've done now is we've lowered the pressure drop across the orifice because we've lessened the driving force at the end here. Instead of 95 pounds, it's 99. So lower flow rate, lower pressure drop across the orifice. So combining GSC theory with fluids theory, keep you sharp on your toes. Okay. Now, I mentioned before using intuition, and I said we want a goal of 200. And earlier I said, well, what if we wanted a goal of 500 gallons per minute? Let's see, 500 gallons per minute. Let's just see. Does that even work in this case? If my normal steady state with a 3-inch orifice got me to 475, is it possible to then increase the size of my orifice to get 500? Well, let's find out. And it's not so much that you would necessarily have intuition that this wouldn't work, but these are things to keep in mind that if GSC doesn't seem to work or is not meeting what meeting the parameters that you expect it to, this could be why. Okay, so I'm going to change my orifice again. Oh, you know what? I don't even need to add one. I'm going to delete that. Yes. And I'm going to reapply that orifice parameter from before. So remember, the goal seek manager is global. It applies to every scenario, but the individual parameters for variables and goals are not global. Those are scenario specific. So I do want a new goal. Volumetric flow rate, 500 gallons per minute by varying my orifice. Again, changing this default that's been happening. Oh, I didn't turn goal seek on when I created this child. That's why this is coming up. A reminder that when you create a child, you need to make sure that it's actually on in use. So here we go. All right, so hey, we can. That's pretty good. Okay, what about 800 gallons? You can see where I'm going with this. Eventually there's a point at which it cannot. And that is, I believe, about 800. So let's check it out. Why not? So we can increase the orifice area, right? No. I'm going to create a child to keep everything separate. 800 gallons per minute. So again, using intuition, 500. Yeah, that makes sense. Why not? Increase the orifice size a little bit to do the opposite of what we were doing. What about now 800? So I can just go through, either add a new goal or edit this one. right? These squares, good, because it's a carbon copy of the one before. Oh, now we've hit a limit. So we cannot get 800 gallons per minute because, well, my orifice can only be so large. It is limited by the size of the pipes connecting. So it says 94 inches. Well, I can tell you that's not a real result because if the pipes are only 4 inches in size, the orifice cannot be that large, and there's no way to force a larger flow rate than the system would allow, if only varying the orifice size. So that's an example of using intuition. 500, sure, sounds reasonable. Maybe, maybe not. 800, certainly not. Apparently it's just too large. Okay, so that is just an overview of GSC in action, a defined goal and changing your variables to meet that goal. All right, so let's get into the proper technique of GSC. Before the GSC module may be used, a Fathom and Arrow model must be runnable. And that's why in that example, the base scenario I ran without GSC to make sure the steady state solution is reasonable and not throwing up any errors. Because if you build a giant model and it's not even runnable in steady state, you're going to see some problems running in GSC. So there it is. A tip, make sure GSC is active and is in use. So you will not see the GSC manager that I was pulling up if you don't first activate the module. So you can do that from the front screen. There are a few different ways to do it, but this is just the easiest way if you're already in the software. Tools, activate modules, GSC. And then that allows you to then, it shows up in analysis, you can go turn it on, put it in use, and then go into the goal seek manager. That's pretty important. You need initial input values in the pipes and junctions, even though GSC will be varying them. So although it will be changing what you put into the junction, you still need to put in your parameter value into those junctions and pipes. Use the intuition to help convergence, what I call smart initial values, which is it ties into running the model before GSC, make sure everything kind of makes sense, and make sure the goals are realistic and they don't counter each other if there are multiple goals. Make sure your variables directly affect the goals. Again, goal must be a function of the variable you are changing. And lastly, this is pretty important, the number of variables should equal the number of goals. 0 degrees of freedom is the key. So if you do any sort of, mass and energy balances of your system, you understand the need for 0 degrees of freedom, because too many variables means it's an under-specified system and there's no unique solution. A quick example is x plus y equals 3. Okay, tell me, what is x and what is y? Well, we can't answer that because there's 1 degree of freedom. We need an extra equation to be able to solve this. So that's an example of too many variables and only one goal, no unique solution. Okay. The other would be too many goals, which is an overspecified system, which is no solution probably unless the two goals happen to already align with one another. So that would be like saying, x equals y, x equals 3, and y equals 2. Well, that doesn't work out so well, let me tell you. That is an overspecified system and it is not solvable. You want exactly 0 degrees of freedom. When using GSC Manager, make sure you have the correct variables and goals applied for each scenario. So you will open the manager and it will look similar in each scenario, except for the apply check mark will be different in each, as long as you are applying different variables and goals to each scenario. Right? What I call global use of the GSC Manager, but the variable and goal is seen in each respective scenario, right? And it's applied differently. Quick tip, double clicking on a parameter line within GSC Manager will open the object's properties window. I had done that previously, so you saw if I double clicked on that line, it popped up my orifice, and that way I could see that it is not just, it's not varying area, it was varying diameter, because that's what I specified in the orifice, because the variable interface in the GSC manager doesn't necessarily tell you what the units are or which specific setting you're varying, because some junctions have multiple. So it helps to really get your mind situated by opening it up, right? To ensure the variable is specified consistently. Now let's get into the control aspect of GSC. So the solution run from GSC run represents the input required to get a parameter, aka your goal, to a certain control set point. Now we're kind of talking about process controls, right? In the first example with GSC to obtain 200 gallons per minute, we are essentially finding the appropriate setting of the manipulated variable orifice size to then get my controlled variable to be what I want it to be the set point, right? And you could have stopped me during that whole initial example I did and say, hey, Walt, why don't you just use a control valve to get 200 gallons per minute? And I'd say, that is a great point. Exactly, you can. So you can kind of make the connection now. Goal seek and control are really two sides of the same coin. Right? I could have just put in a control valve there, and I would have seen the same pressure loss across that junction as I did across the orifice, because what a control valve would do is vary its losses until my set point is reached, kind of like what GSC does, right? It would have gotten me the same system behavior as using the right size orifice does. But, and this is a big but, control valve junctions directly control only 4 parameters. That is downstream pressure, upstream pressure, pressure drop, and flow rate. Also, this implies they only directly control parameters nearby, meaning right adjacent to the junction. Right? What if I wanted to control temperature downstream of a heat exchanger? What if I wanted to control velocity? Right. Well, a control valve does not have that capability. That's where GSC comes into play. It extends the versatility of Fathom so you can achieve process control, right? Well, I could manually iterate on the control valve set point to find what flow rate yields the set point temperature, but I don't want to do that, right? I live in the 21st century. I'd like my computer to do that. So let's go through an example, another one for process control specifically. We've got hot water coming in from a steam trap that we want to cool down for a process downstream. So here we go, reservoir up, pumping, and we've got these heat exchangers here, and we got a bypass line. And what we're going to do is vary essentially the flow through this bypass line to get 120 degrees as my outlet leading into the reservoir for the process downstream. So controlled variable, temperature downstream, manipulated variable, flow rate upstream of this bypass. And we're going to do that in a very unique way because you can see there's no control valve here. So let's go open it up. Yes. If you run multiple instances of Fathom, you might see that message about a user log. Totally okay, not an error. It just logs a new entry in the back end. So just so you know, while I'm loading this up. Okay. So here we go. We've got our example. So we're going from a reservoir through a pump to some heat exchanger, a couple of them in parallel, and we are defining this via defining the parameters of the heat exchanger, not just a specified heat rate. An inlet temperature of 40 degrees looks like it's going to be water because specific heat is a 1. So, okay, let's run this as is. Hey, we get a warning. That doesn't look so good, but don't be alarmed. That's why it's always important to read the warnings. See, HGL and EGL may not be meaningful because of variable density systems. That's because I have heat transfer on in this model. And hydraulic grade line and energy grade line are essentially energy in terms of head, And with density changing, that doesn't mean so much. So you really want to just kind of look at pressure in these types of systems. Anyway, an example of don't just be freaked out by a warning. Okay. Now let's go through some GSC 120 degrees F. That's my goal, right? Okay. So again, it's a carbon copy when I make a child. So it's assumed I've already run everything. You see, I don't have my goal seek on. Go. Already an entry. I say yes. Use. All right. So now I'm going to goal seek. What can I vary to make sure this is 120? Well, you know what? I didn't even show you what the temperature was before. Why don't we do that? Sorry, I've forgotten. Temperature downstream in pipe 10. 128 about degrees Fahrenheit. It's a little too hot for me. So at least we're kind of close, right? Well, let's see if we can use GSC to control that temperature. So variable, what can I vary? I'm going to vary the open percent of this three-way valve to direct either more or less flow that way. Three-way valve, open percentage, good. Goal, my goal is a point pipe, not volumetric flow rate anymore, temperature, 120 degrees. Inlet, yep, perfect. And if it was too hot already, do you think we need more or less flow? Well, we probably need less flow through the bypass because that's at the hotter temperature. So if we get less flow through here, we're going to get a smaller temperature. Probably. Why don't we go ahead and run it? Warnings exist. Again, don't be alarmed. Oh, user goal is specified 120, final goal result. Oh, you know what? I'll be darned. This is a good example of troubleshooting live, folks. I did not specify the pipe correctly. I specified pipe 1, which is upstream. That's never going to change because my reservoir is 200. Example of this variable does not affect this goal. So the goal is not a function of that variable. So pipe, not P1, P10 downstream. That's what I want. And just to make sure, least squares, good. And now we're talking. Okay, I get that same error, but this time we actually did solve for an answer. My variable, oh, my valve needs to be open 86% of the way, directing more flow through the heat exchanger than through the bypass. My goal was reached. So that's an example of process control. Control variable, manipulated variable. Okay, so another thing I can do is put in a control valve here in this bypass, right? And then change the control valve set point until I reach my temperature of 120 degrees. Another example of using GSC, this time with a control valve specifically, relating process controls back to goal seeking. Okay, well, I'm not going to do that because for the case of time, I'm just not going to, but I will show you something else, linking variables. So maybe instead of changing my valve set point to get my controlled temperature, what if I changed my heat exchanger junction? And I don't want to choose loss factor. I want to choose my secondary inlet temperature. This is a reason why you may want to open up a junction by double clicking, because there are so many different thermal models that it's good to make sure you know which one you're using. So secondary inlet temperature is actually, it makes sense, it's consistent. What I want to do is link these two together. There's two heat exchangers, what I'm showing you here. So the first one is J5, that's my upper one. J6 will be my lower one. I also want to vary the secondary inlet temperature. And let's see, apply my goal. Now, do you already foresee a problem? Because I sure do. What is it? 2 variables, 1 goal, 1 degree of freedom? Well, that is not a good approach. It is possible you get an answer, sure. Is it a unique solution? No. So this message comes up, and in essence, we don't need to read it. Well, dang it, I didn't want to say okay. But anyway, these 2 variables, to make sure that they are essentially one variable, by getting rid of that degree of freedom, I'm going to link it to the other heat exchanger. What this means is that both variables are going to be varied together, and they are they have to be the same value. They are not independent of one another to get my goal. Okay. Oh, I didn't turn it on. Classic. Okay. So that's an example of having 2 variables where you could solve it and I would get an answer, but it's not unique, and an example of linking variables together when you know they should be the same value to get rid of that degree of freedom. Do you see we don't have any warnings about GSC, just the hydraulic grade line? My variables, oh, so my fluid coming in, which was water, was actually 40 degrees Fahrenheit. Now I need it to be 23 degrees Fahrenheit to get my same outlet temperature, right? Within a certain tolerance. And something to note here is that when I get my answers, it doesn't actually change the input value, right? What does it do? It keeps the same model data, input data, but the output is presented as if this was the true input. And that's a way to keep the same inputs, so you know what you originally had, and now you have this, the output represents this. The goal seek answers and any graph results or visual report results will show that. Okay. So another thing that I could be doing would be to do a differential goal. Difference goal, okay. I want to vary, you know what, I'm gonna keep the same variable. I'm gonna vary my 3-way valve again, but to get a different goal. What if we did a differential goal saying that the flow rates need to be 100 gallons per minute different, right? Which means the flow rate of object 1, P1, or not P1, this would be, shucks. I need to just cancel out of that because I didn't label my pipes. This is P2, P3, and P9, I want to say. P9, there it is. Okay, so my differential goal, again, P volumetric flow rate is 100, and this is a difference goal, right? So the difference between P3 and P9 has to be 100 gallons per minute because it does object 1 minus object 2. So if I run it this way, yes, I need to turn it on. I always forget. Terrible during a webinar. That's an example of a differential goal where instead of just a single point in the system like that temperature, I am now trying to have a certain flow split, right? So you can see with how many times it's running, it's calling that hydraulic solver again, and it will eventually then convert on an answer. There we go. Hey, my goal, 100 gallons per minute. It converged on 99.97. I'd call that good. And it needs to have a open percent now of 65%. So that's an example of a differential goal. You can kind of start to see the power of GSC, I hope. All right. Okay, so as I said, getting the answers from running GSC does not replace your original input, but it does report the output parameters according to the inputs found from GSC, essentially saying it runs the model as if GSC answers were the input because it goes through that hydraulic solver and that final GSC variable that got me the goal, that converged on my goal is now the output. But it doesn't actually replace the input on the workspace or model data when you're looking at it. Through the interface there. So what you can do is create a child scenario to use the pin option to replace the input as the GSC. The reason you want to create a child is so that you do not change what is in your original scenario because you probably want to keep that data, right? Or you can create a disconnected scenario if you'd like to isolate the answers for record purposes to make sure you don't accidentally get rid of your GSC answers if you're changing things up the scale of the scenario manager. So that looks like, if I'm in here, output, so if I create a child, so output, oh, I didn't spell that correctly, that's okay. Now that it's a carbon copy of the one above it, but I can go here and pin transfer results to initial guesses. What this does is it transfers over my GSC data into my input, and also all of the other converged on answers will then replace the initial guesses to kind of just speed up the hydraulic solver. This one is a little different of a topic, but the point is here you can put in your GSC answers into your input. So if I say okie dokie, it tells me, well, now it's a different scenario, so it's not the same. I don't have the output anymore. Well, let's go check out, what did I do? The three-way valve. Now you can see that actual open percent here is defined differently than it was in the scenario above. Another example of keeping your GSC variables is to create a disconnected scenario, calling it disconnected scenario. And you can see this because it has a little asterisk there. Now it's totally disconnected, meaning if I change anything up here in any of these, it will not get affected down here. Again, a way to preserve your answers. And when you do that, lo and behold, it takes the GSC, oh, maybe not. Oh, that's because I'm in the wrong scenario, sorry, it should. The big reveal now, even more intense. Ah, there it is. It took my answer and put it in the input. All right, so as we said, it saves it from being modified accidentally. So now there's a difference between Fathom and Arrow. I've only gone through Fathom, right? But with AFT Arrow, for all of you Arrow users, it's the same logic, it's the same tool, but compressible flow analysis has inherently unique aspects compared to incompressible flow. So AFT Fathom is the incompressible flow analysis. AFT Arrow is compressible flow, different software program. And there are extra complications with density changing with pressure and temperature using an equation of state. So volumetric flow rate is not constant down a pipe, right? Because you have changing density. Mass flow rate is, but in essence, there are more coupled parameters to consider. So there are some unique variables and goals in Arrow that you will not see in Fathom. Things like enthalpy, Mach number, degree superheat, stagnation temperature, things that are unique to compressible flow you will not see. You must also understand the implications of using similar parameters in AFT Arrow, like point parameter becomes very important because the parameter may not be constant down the pipe, such as a velocity. In Fathom, velocity is constant down a pipe if it's the same cross-sectional area. In Arrow, velocity is not constant down a pipe because it's got changing pressure and temperature, density. So velocity will actually increase down the pipe. So choosing your point becomes very important. Right. Okay, well, let's go through an example. All right, so here we've got a natural gas burner, right? we need a delivery temp of 100 degrees stagnation down here. And what we have here is methane in the supply tank going through a heat exchanger, getting heated up, ready to go through to these burners. And what we want to do is vary something to get my desired goal of 100 degrees stagnation temperature. All right, so pulling up the model now. All right, here we go. So always make sure the model is runnable, right? So I've got methane in here, as I said, 500 pounds, 50 degrees Fahrenheit. Well, in order to get 100 degrees out here, I'm gonna have to heat it up, right? So through my heat exchanger, got a specified heat rate in, and that sneak preview, that will be what I vary to get my outlet temperature to be what I want it to be. But as always, run the scenario first. Okay, and it works. Excellent. That's what I like to see. Go back to the workspace and let's make sure our temperature is not already what we want it to be, right? So my temperature stagnation out is 64 degrees. Well, I wanted it 100 degrees. So I've got to put more heat in here. And if you're wondering what the heck is the difference between static and stagnation temperature, it has to do with flow energy being accounted for. Topic for another time, but something unique to compressible flow. Okay, so GSC, we're going to go to heat. Heat rates we will vary. Okay, so I'm getting ready for GSC, but first you need to activate the module. I want you to get used to this because it's so common to not remember. I do it all the time. Okay, so we're getting ready, but you maybe already foresee a problem. If I vary too many parameters at once, I will have an underspecified system with a, or sorry, the other way. If I only have one variable, the heat rate in, and many goals, I've overspecified the system, and I can't meet every single goal. Probably, that's almost every system will have that, unless there's some reason that they would be the same. In this case, we can't. So this brings us to the topic of group goals, right? A goal can be applied to a group of objects at the same time. So all of those pipes can be one goal. In order to use a group goal, all of the objects must be added to a group by using the groups command on the edit menu. There are two types of group goals. There's the sum, which takes the value for each one of the objects in the group and adds it up and says it needs to be this value. A group max or min will specify the maximum or minimum value that can be met in all objects of the group. And you'll see there's nothing here that says just goal. There's not a single value goal because that would be an overspecified system. So rather with group goals, you can only specify a maximum or a minimum to allow a little bit of difference between each of the goals, but still above some value that you set, right? So specified by an inequality rather than an actual answer, similar to having more goals than variables, but will likely not be able to achieve that many desired values. So it's a threshold instead. Okay. Now, let's go run it. Oh, as I said, you need to create the group first. So I highlight all the pipes, go to Edit, Groups, Create, Discharge. And it's got all my pipes highlighted. Okay, I've created that group. Now I go into Goal Seek. Okay, I'm going to vary my heat exchanger. Remember, it is a heat rate. It's not an inlet temperature like before. Again, double clicking helps us figure that out because it's a specified heat rate there. Okay, goal is no longer a point or differential goal. It's a group goal. And I want a max min of temperature stagnation, right? I want greater than or equal to 100 degrees Fahrenheit for each of these pipes. And I want the object, the group is called discharge, but I don't want the inlet, I want the outlet, right? So it has to at least be 100, not exactly 100, but a minimum of 100, right? Okay. Well, let's run this and see what happens. Before we go too far, want to let you know a little secret about the GSC solver. You see this number is 999. That's the best. We want that number to be 0. So if that number is not approaching 0, we know we have a problem. So again, that's a spoiler alert. It did not reach 0. In all the other runs, you can go back, you'll see it goes, below 1, 0.02 or 0.3. Well, that's an indication that I already know there's a warning, not only because I prepared the webinar, but because of that number. So we couldn't actually reach our goal. So my variable stayed the same. It didn't even change it. Okay. Well, that's weird. And my actual value is 64. Well, that's no different than it was before, right? Go back to the warning. Let's read what it says. GSC goal may not be valid, right? Recommendation, change solution control tolerances and goal seek control parameters. So we can do that automatically, but I want to go through something else first. And that's when this topic comes into play. When goals cannot be achieved. Some cases, GSC module may not be able to achieve a goal. This can happen because a goal is not physically realistic. In our case, it probably is realistic because I can just increase the heat rate until I get my temperature. A better starting point is needed for the input values assigned as GSC variables, meaning I need a better guess for my heat rate in. And that's usually because there are so many coupled parameters in something like Arrow that having a better guess, it gives direction to the solver, right? Or the hydraulic solution tolerances or optimizer numerical parameters require adjustment. And that's that warning we got earlier, right? So before I go too far, let me get back to Arrow real quick. So what I could have done, right? Chose this to be 1000 BTUs per second. Why not? I just doubled it, right? And this is my idea of a better guess. And again, you can see we're still at 1000. Okay, well, that's not very good. Not yet, at least. Maybe I'll take some time to talk about the solver in general too, since it's going to take a little while to run. Oh, here, look, we've got it going down. Well, that's a good sign, right? Okay, but in general, the hydraulic solver here, most of you probably just stare at the runtime when you're looking at it, but it does provide some useful information if you ever want to go through it. The idea is that pressure, mass flow, enthalpy, and concentration all have to be solved for to get a solution. So these numbers represent how much they're changing with each iteration. So you can see pressure and mass flow are not changing at all. They're at 0, which means they've come to their answer essentially. Now enthalpy is changing a little bit, but it's within a good tolerance. Okay. And now we finally got an answer. Let's see what it says. Hey, whoa, we got an answer. But did you see that was at like 500, that convergence, right? Well, let's see how close. Okay, well, it varied to 1001, but did it get my goal? Hey, it actually got my goal pretty well. That large variance there is probably because tying an energy balance to this system is very complex, and it maybe doesn't need as tight of a tolerance or as tight of an answer. Making a change does not affect it as much, or there's other implications of affecting a change, so it found an answer without having to go all the way down to 0. But guess what? I already knew the answer was about 1000 BTUs per second. That's why I put in the guess. You're thinking, well, how the heck would I have known it was 1000? That's a good question. You wouldn't. That's where changing the numerical optimizer, determines the goal search directions by approximating gradient based on perturbed variable values. Essentially what I'm saying is you can change things in the solution control of GSC to help this solution go your way, essentially. By default, it uses a central difference approximation, but forward difference can also be used. What does that mean? Okay, well, I don't want to go too far into this for the sake of time, but essentially central difference is the default. We've got an actual objective curve, and we've got an approximated slope generated by GSC. And if we're landing at a value right here from our steady state, we are going to perturb a variable and see what the change is and see if we actually line up better with our objective curve, which is our goal. And it does that forward and backward. That's why it's a central difference. It's a small deviation in each direction, perturbation. Forward difference is similar, but it just goes forward, a forward perturbation. Again, the default is central, but forward is also a possibility. But the idea is it's changing the variable until it meets until it matches up with this objective function curve within a certain tolerance, right? So a cause for this could be if the hydraulic solution is not converged to a sufficiently small tolerance, the gradient approximation will not be sufficiently accurate. What I'm saying is if the hydraulic normal steady state solver does not have a very tightly held answer, then a good search direction for goal seeking fails. So there are two general areas that can be changed. There's the hydraulic solution tolerances and solution control. This is your normal Fathom solution control. Then there's the numerical control parameters in the GSC manager. Oh, too far. There we go. Okay, so when we went, I'm going to create a different scenario. So changing solution, I'll just say changing numerical control because there are two types, remember, solution control and base AFT Arrow. Sorry, I might have been speaking about Fathom. It's the same in both, but anyway, there's numerical control in the base software, and then there is GSC control. Okay, so again, let's go through here. I'm going to apply this. I want to rerun it with the same. Oh, I didn't turn it on. Gosh, I always do that when I make children's scenarios. I'll run it the same as before. We're going to get the same error, and we're going to see what the options are that it prompts us to do. And this is always going to be the best option for you as a user without understanding completely how the hydraulics solver and GSC solver works. It's best to just keep with the suggestion of Arrow. So again, it's solving right 9 and 9. Probably not the best answer, right? Oh, there's the error that we saw before. That's where pressing F2 to automatically adjust parameters. That's very helpful because we press F2, I can change both the GSC solution method and the solution control tolerances, which again, one is for GSC, the other is for your base AFT Arrow, right? So I'm going to change both. By making it a tighter tolerance, I might be able to converge on an answer, right? Okay, so here's solution control that I was talking about before. This is just base AFT Arrow. Tolerance, I've tightened them up. So the Arrow default is actually e to the -4, but we had it e to the -5. I'm going to cancel out to not save it. GSC control manager, what it's done is change this finite difference step to be a little bigger so it can see a more dramatic change and get a better direction for how it should solve. And let's see how that affects. Again, without having a better guess for my heat exchanger, I might be able to see convergence on an answer. Like I said earlier, you don't necessarily, the point of using GSC is that you don't know the answer already. So putting in a better guess, it's not always helpful, but if you've got some intuition about your system, it may prove helpful. So you can see, hey, we're already kind of getting down there, even better than having what I would call a better guess, right? 22, wow, not too bad. You got to be patient with Arrow, being a more complicated type of system with compressible flow and all the changing parameters. It tends to run a little bit longer. For any of you Arrow users out there, you may know that. For anybody who uses Fathom and is looking into Arrow, perhaps for some projects, just know that takes some patience and calibration. Sometimes more than other times. Oh, there we go. Now we're talking. Well, I guess I should apologize in advance. I did not expect it to run this long, so my apologies for all of you watching at home. But it should be over soon. I assure you, I've run this a few times. Oh, there we go. Record time, 2 minutes and 13 seconds. Again, sorry about that. But the point is I wanted to show you how it can help, and it did. And we got rid of our error. We got our variable 998.8, so right about 1,000. That's how I knew what my better guess should be. Now we've got a delivery temp of 100. So you can see that here. Let's see, outlet 100 degrees. Let's go to our, get a list of these temperatures. 100, 100.5, 100.8, 100.5. So remember, again, the point was a group goal. So not all of them are exactly 100, but the minimum is 100, and the rest are a little higher than that. So that's an example of group goal and some troubleshooting tips. And as we get this show to a close, I want to bring up a case study of a desulfurization system that was optimized using Arrow and GSC. And it was in Poland, but the big idea was that there are environmental regulations that require this power plant to expand their flue gas desulfurization system, and they needed to ensure a controlled pressure at the furnace exit, which is the inlet of the model, but the furnace exit. They used Arrow with GSC Module to find the optimum fan conditions, and the engineers were able to creatively model the unique aspects of the design, which I will show you. And the solution was they found the fans should provide about 300 pascals of pressurized to ensure the proper furnace exit pressure while maintaining expansion demand to meet regulations. So here we go. This is an Arrow model. Hopefully it's not too overwhelming, but the idea is we got inlet down here. These are the furnace exits, right? So they had to expand and put in more of these. And with that, they had to put in new lines. That's what these blue lines are, and some new stacks over here. So if we look in the top right, these new stacks, what they did was they modeled natural draft outside of these stacks as fans with flow and pressure data, which is very creative. They were able to find the data of pressure change at certain flow rates and to model both cold and hot weather. So that was really unique. And then the desulfurization was modeled as heat exchangers and spray junctions. Since Arrow is not used for chemical reactions and necessarily getting into that detail with processes, but you can still model things like they did with heat exchanger and spray junction to model the water that would be coming in during desulfurization and then coming out the stacks, obviously. And the main point of GSC was down here to the bottom middle, furnace exit. So they found that a pressure rise of about 3,000 pascals through these fans would give them their desired furnace exit pressure. Again, specified goal, -40 pascals of gauge. They needed 3,000 pascals pressure rise to obtain that. Okay. And this one's a lot quicker, I can assure you, so don't worry too much. Yes, again, it's asking me because I ran another instance of Arrow, just a user tip. If you see that, you can just say yes, and it's okay. It's always good to see a real system in action, since a lot of these were examples. To really show you that this is not just for examples and for theory, but people actually do use this for systems. All right, here we go. So this is the real system that they had built, right? Again, we got flow rate coming in out of these furnaces, right? And the fans moving the fluid through these, through their ducting system to then go out to their stack after desulfurization, right? So what did they do? Let's see. Goal, seek, and control. Whoa, now you can kind of see the power of GSC. They had so many variables and a few goals. The way they could do this is because they were linking, right? So each of these compressor or fans were linked together so that they would have the same value. But that's all they were doing, was varying the compressor values, the pressure rise, until they got their goal, which was each of these outlets of the furnaces should be this pressure. So again, goal, outlet pressure of the furnace, inlet of the model, and the variable would be the the fan pressure rise. Now let's see how Arrow performs. So we got the first run of GSC, excellent. Again, it's running multiple variables, but they're linked together so that the degrees of freedom do work out. But you can see we're kind of converging pretty quickly, going from 999 like that last model we were showing, down here to just about 1. All right, still took a little longer than I expected. Sorry about that. Expected it to be a little faster. But hey, we've got answers, and these cautions up here mean that there is some negative flow through the sprays because, as I had mentioned earlier, they were modeling flow in anyway, so that's to be expected. An example of interpreting the cautions and warnings that you get when running a model, but it converged, and let's see our variables. So each compressor was given a specific value of pressure rise in order to get the goal of negative 40 pascals of the furnace outlet, and they actually use this to then create their expansion, their power plant expansion to take on more desulfurization and thus meet the regulations. That is GSC at work in a real system and shows the power of it. So thank you guys so much for staying here with me. I know we ran a little long. Sorry, I get a little excited about our modules. But just so you know, here's a list of all of our products. We have 3 software, base software programs. I didn't mention Impulse because GSC is not a module. But again, we got Fathom and Arrow, Impulse. We have Utility Chempack, which expands your property or your fluid database, and you can get access to about 600 fluids with more data and all that. We also provide consulting services to help when you are in a bind and need help quickly. So thank you again for watching. Here's our contact information page. I will leave that here for a sec. If you guys have any questions, you can always reach out. Thank you again. Have a great day.